Good day. Section number 6, using rational zeros to find solutions. Ultimately, what's happening here today is we are going to find solutions of an equation when we don't know any solutions. As an example, yesterday we found solutions to an equation when we knew one of the solutions. As you can see, this example I'm going to start off today with. We know that -5 is a solution. So this is a review of what I talked about for today. We know -5 is a solution. We are going to put that into our synthetic division. We're going to divide by it. We should get a remainder of 0 when we do this. So drop the first number, multiply -5 times that 1, you get -5. Add those numbers, you get 0. -5 times 0 is 0. Add those, you get -1. -5 times -1 is 5. We add those together, we get 0. We should get a remainder of 0. That's good. That means that's a solution. Then we have to decode these numbers below here. This says we have x squared plus 0x. Keep in mind that's the x term. This is the x squared term. And then minus 1. And that's going to equal 0. We want to find the zeros, the remaining zeros, or the remaining factors, okay? So anyway, x squared minus 1 is what remains. That is factorable into the sum and difference of its square roots. Keep in mind, if -5 was a solution, x plus 5 would be the other factor. So if we are asking for the factors to this polynomial, there would be our factors. If we're asked for the zeros of this polynomial, we set each one of our factors equal to 0. We find -1, 1, and -5. Today, we are going to, like I said, find the solutions to a polynomial when we don't know any of the solutions. So we're going to kind of be in the dark. We won't know anything. We're just going to have to guess. But I do have some options for us to help us, okay? And it's called the rational root theorem. The rational root theorem. Here we go. The rational root theorem gives us the ability to come up with a shortened list of every possible number in the world that could work. Because right now, if I don't know any possible solutions of something, I simply have every number in the world to choose from. The rational root theorem allows us to narrow that list down. There's two components to the rational root theorem. There's the p-values, which are all the factors of the constant term, and then there's all the q-values, which are the factors of the lead coefficient. Let's take this first problem here on the left. Find the possible rational roots of this expression. Okay, so I forgot what we're going to do. I forgot to tell you what we're going to do with these. We're going to take all the possibilities of p divided by q. That's going to be our possible rational roots. Simply the possible solutions, not the actual solutions, just the possible solutions. As I've said before, roots, solutions, zeros, x-intercepts, they're all the same things. So let's put this in action. Let's take this one on the left. Y to the fourth minus 10y to the third minus 10y squared plus 5y plus 6. First of all, the degree of your polynomial will tell you how many solutions we can expect in this problem. So we have a degree of 4. That means there are going to be at most 4 solutions. FYI. Anyway, so this first one here, we're going to find all the factors of our p-value. Now 6 is our constant term, so all the possible outcomes of the factors of 6. And that's always going to be plus and minuses, because you can take 1 times 6 or negative 1, 1 times 6 or negative 1 times negative 6. They both produce 6. So plus and minus 1, plus and minus 2, plus and minus 3, and plus and minus 6 are all the factors for the constant term. And then Q, the lead coefficient, in front here is 1. So factors of 1 are 1 and negative 1. And what we're looking for is all the possible outcomes of P divided by Q. So that's all the P values divided by all the Q values. So that's 1 divided by 1, 2 divided by 1, 3 divided by 1, and 6 divided by 1. And we have the possible solutions, rational solutions. This doesn't involve the irrational solutions, but all the possible rational solutions of that equation. Let's go to this next one. Possible rational roots of that expression. I'm going to slide some things over a little bit here, give myself some more room. We want that problem to move over just a little bit. There we go. So here we go. We're going to do this again. I'll just come off to the side here. Figure out what the p-values are. P comes from the constant term. So factors of 3 are 1 and 3. Nice. Q comes from the lead coefficient. Factors of 13, 1 and 13. And so we're looking for all the possible outcomes of P divided by Q. Here you go. P over Q, you got 1 over 1, gives you 1. Then you have 3 over 1, gives you 3 over 1, which is 3. I didn't write that very nicely. There we go. Next, we have to put everything over 13. So we're going to put 1 over 13. And then we're going to put 3 over 13. And there it is, all the possible outcomes of P divided by Q. Those are your possible solutions to this equation. Possible rational solutions. You've got to clarify, these are just the rational solutions, not the irrational ones. The irrational ones are square roots and such, and we won't be able to find those through any means like this. But it gives us a narrow list of possible outcomes. So now onward to actually doing one of these. All right, so now we want to find all the zeros of a function, and we don't know anything about this. So this one is no different than this first one I started with, but this first one I was given a little hint that -5 was actually a solution. I have no hints on this problem, so I simply have to try and try and try until I find a possible solution. What we can do is perform the rational root theorem of all the possible P over Q values. Keep in mind Q is the lead coefficient, which is 1, and then P comes from the constant terms, factors of 24. 1, 2, 3, 4, 6, 8, 12, and 24. And so we're looking at all the possible outcomes of P divided by Q, which is just going to be P in this problem. So keep in mind, when Q is 1 or -1, your P over Q values are simply what your P values are. So it can be very efficient to do that. We have only one option in this problem, and that is to try. We can't do anything magical. All we can do is try and try and try until we find a solution. So we're going to try 1 and see if it works by synthetic division. And you see that we didn't get a remainder of 0, so we know 1 did not work. So that means we're going to go down the list and we're going to try -1 next. And I have to try until I find a solution. And so this could be a very painful process, and it could turn out that I might find one very, very quickly here that works. negative 5 for remainder. That didn't work. Okay, so let's move this up a little bit. I can fit another one in down here. Let's try the next one. Let's go on to 2. And sometimes you'll find that 1 works, and hip hip hooray, yay for us. We got ourselves a solution. So let's see, maybe this one will be the magic one. It's not looking like it's going to be. Negative 20, this is negative 44. 2 did not work. So I keep going. Now look at, I'm just going right down my list here. Negative 2 is my next number that I'm going to try. 1, 2, negative 18, negative 24. Drop the first number, multiply, add, that's negative 4, multiply, that gives me 8, that gives me negative 10, multiply, gives me 20, gives me negative 4, that didn't work. I'm on to 3, let's hope 3 works. One, 3, 5, 15, negative 3, negative 9, negative 33, doesn't matter, it doesn't 0, we have to have 0 there, so let's try negative 3. 1, 2, negative 18, negative 24, 1, negative 3, negative 1, 3, negative 15, 45, 21, negative 3 did not work. That means I'm on to the magical number 4. Move my screen a little bit. See if we can find another one. That might work. We haven't found one yet. We're going to keep trying though. 4. 1, 4, add them, you get 6. Multiply, you get 24. Add them, you get 6. Multiply, you get 24. And we finally found a solution to our problem. We know one of our solutions is 4. It means that came from a factor of x minus 4, by the way. Now, what remains is x squared plus 6x plus 6. We would hope that we can factor that, but it is not factorable, so we're going to find the rest of our solutions by completing the square or quadratic formula. I'm going to complete the square for you in this problem. Move the constant to the other side, take half of the middle coefficient and square it, add to both sides, factor the left side, that's x plus 3, the quantity squared, equals 3, and solve by square rooting both sides. We get plus and minus square root of 3, x equals negative 3 plus and minus the square root of 3. Along with our solution we found of 4, there is our solutions. So as you can see, that one took a little time, many attempts to find the solution. So let's try that again. Let's go down to this question here. Make that print a little bit smaller. Here we go. We're going to try this again. Same process. Keep in mind, we got the factors of 6 divided by factors of 8 as possible solutions to this problem. So here we are trying again. I'm going to use my crystal ball and give 2 a try. And let's see what happens when I plug that number in. I get 16, 14, 28, 3, and 6. I love my crystal ball. Gives me a nice little answer right away. 8x squared plus 14x plus 3 is what's left. We would hope that we can factor that. I'm not sure that it is factorable. So we're going to use a little quadratic formula to see. Actually, I think it is factorable. Now that I look at it, we got 4x and 2x, plus and 3 and 1. That gives us 14x. And so our factored form for this is x minus 2. Our solutions are negative 1/4, negative 3/2, and 2. And there it is, factored form and your solutions. Thank you. Hopefully this makes sense. and have a great day.